In 1936, a 24-year-old proved that there are questions no computer will ever answer. Not the computers we had then, not the ones we have now, not the artificial intelligence everybody is racing to build. Any machine, running any program, for as long as you like. And you have already run into this limit, probably this week. A progress bar. 2 minutes remaining, then 17 minutes, then 4, then it stops at 99% and tells you, unknown. Now think about how strange that actually is. Your computer has the entire program in front of it. Every line of code. It knows exactly what hardware it is running on, how fast the disk is, how much memory it has. It has more information about this task than you will ever have about anything. So why can it not simply look at the work and tell you how long the work will take? And notice this is not a case of one badly written installer. Every operating system does it. Every company, every decade, with every improvement in hardware, and the bar still lies. 60 years of the best engineers alive have not fixed it, which should tell you it is not the kind of thing that gets fixed. The honest answer is not that the engineers were lazy. It is not that the estimate is merely hard to compute. It is that a general solution to that problem is mathematically impossible, and a young mathematician proved it before the first electronic computer had been switched on. Before the proof, one more everyday version of the same wall, because it is worth feeling it in your own kitchen. You want to reheat last night's food. How long do you put it in for? You could guess. 2 minutes. You could guess more carefully. It is a thick dish, a deep bowl, call it 3. Or you could be systematic. 30 seconds. Check it. Still cold in the middle. Another 30. Check again. Getting there. 10 more. Notice what that careful strategy actually does. It gets you closer. It never gives you the number. There is no formula you could be handed that would tell you the exact time for any dish, in any container, at any starting temperature. Too many variables, and the moment you think you have covered them all, somebody puts a frozen block in a shallow dish, and you are checking every 30 seconds again. That feels like a practical problem, a matter of not having enough information. It is not, and that is what Turing proved. Here is the whole argument. It takes about 90 seconds, and you do not need any mathematics to follow it. Suppose somebody hands you a perfect program. Call it Halt. You can feed Halt any piece of code you like, along with whatever input that code is going to run on, and Halt will tell you, correctly, every single time, one of two things. Either this program eventually finishes, or it runs forever. That is all Halt does. It never guesses. It never says maybe. It is always right. Now we build a second program, and this one is deliberately obnoxious. Call it Rebel. Rebel is very simple. It contains a copy of Halt. It looks at Halt's prediction, and then it does the opposite. If Halt says the program finishes, Rebel loops forever. If Halt says the program runs forever, Rebel stops immediately. Now put those two together into one program and call the whole thing Paradox. And then do the one thing you were always going to do. Feed Paradox its own source code. Follow it through. Halt looks at Paradox and has to make a call. Suppose Halt says, this program runs forever. But Rebel is watching that prediction, and Rebel does the opposite, so Paradox stops. Halt was wrong. So suppose instead Halt says, this program finishes. Rebel sees that, does the opposite, and loops forever. Halt was wrong again. There is no third option. Whatever Halt says about Paradox is false the moment it says it. And notice we did not make a mistake anywhere in the construction. Rebel is trivial. Combining two programs is trivial. Handing a program its own code is trivial. You do it every time you open a text editor in the text editor. The only thing in that chain that could possibly be wrong is the thing we assumed at the start. Halt cannot exist. And it is worth naming exactly where the trap is, because it is not in the mathematics. There is no clever algebra in that argument. The whole thing turns on one move. We let a program read its own description. That is not an exotic thing to do. A compiler reads code, and a compiler is code. An operating system manages programs, and it is a program. The moment a system is general enough to be handed any code at all, it is general enough to be handed itself, and once that door is open, you cannot close it selectively. That style of argument has a name: proof by contradiction. You assume the thing you want to disprove, you follow it carefully until it contradicts itself, and the assumption is what breaks. It can feel like a trick the first time you see it. It is not. It is one of the oldest tools in mathematics, and it is how we know there is no largest prime number and no fraction that squares to 2. But be careful about what has just been proved, because this gets misquoted constantly. It has not been proved that you cannot tell whether a program stops. You can, very often. Look at a loop that counts to 10 and you know. Look at a loop that adds 1 forever and you know. What has been proved is that there is no single method that works for every program. No universal test. Build any procedure you like, however clever, however long you let it run, and there will be programs it cannot decide. Turing published that in 1936, before there was a computer to run anything on. Alonzo Church had reached the same wall independently, from a completely different direction, at almost the same moment. The name we use now, the halting problem, came later, decades after the fact. And it is the reason your progress bar lies to you. To tell you how long the installation will take, the installer would have to work out in advance how long a piece of code is going to run. Not this code specifically. Any code, in general. That is precisely the thing that cannot be done. Now, you might reasonably think this is one narrow question about stopping. An awkward corner case. Everything else about a program can still be worked out. In 1951, a mathematician named Henry Gordon Rice proved that it is not a corner case at all. It is the shape of the whole subject. Rice's theorem says, roughly, no general method can determine any interesting property of what a program actually does. Let me unpack that with an example rather than a definition. Imagine every country runs its defense systems on software, and one country finally builds the thing everybody wanted, a program called Oracle. Feed Oracle another country's system and Oracle tells you, reliably, whether that system is peaceful or hostile. Now a rival country builds a system of its own. Call it Mirage, and Mirage has one instruction written into it. Find out what Oracle says about you, and be the other thing. If Oracle judges Mirage peaceful, Mirage launches. If Oracle judges Mirage hostile, Mirage stands down and offers a treaty. It is the same trap, wearing different clothes. Oracle cannot be right about Mirage, and Mirage is not a strange or unnatural program. It is a perfectly ordinary system that happens to read a report about itself. Rice's theorem makes that precise. It distinguishes two kinds of question you can ask about a program. You can ask about its text, how many lines, which letters, whether it contains a semicolon. Those are easy. You just look. Or you can ask about its behavior, what it will actually do when you run it. Is it safe? Does it ever leak this file? Will it always give the right answer? Does it stop? Rice proved that every question of the second kind, as long as the answer is yes for some programs and no for others, has no general method. Not a hard one. None. And that puts the halting problem in its proper place. It is not the exception. It is one instance of a much larger rule, and stopping just happens to be the easiest instance to state, which is worth sitting with for a second, because we ask questions of the second kind constantly. Is this software secure? Does this system do what it claims? Will this thing behave itself in a situation nobody thought to test? We can answer those questions in enormous numbers of specific cases. We do it every day. What we cannot do is build the machine that answers them all. So far, every limit has been about impossibility. There is a second kind of wall, and it is arguably more brutal, because the answer is right there and you still cannot have it. Here is a problem a child can state. You have a list of cities. Visit each one exactly once, come back to where you started, and take the shortest route you can. That is the traveling salesman problem, and there is nothing impossible about it. The best route exists. It is a specific route. You could point at it. So find it by brute force. Check every possible order. Measure each one. Keep the shortest. 10 cities. Once you account for the fact that a route is the same route whether you drive it forwards or backwards, and it does not matter which city you call the start, there are 181,440 different tours. A computer checking 1 billion routes a second finishes that before you have let go of the mouse. Now 20 cities. Only 10 more. 60 quadrillion tours. 60 million billion. Our billion-a-second computer is now going to be busy for about 2 years. Now 30 cities. 4.4 times 10 to the 30. 4,000 billion tours. The same computer, running without stopping, would need roughly 140 trillion years, about 10,000 times the age of the universe. 30 cities. You could name 30 cities in under a minute. And nothing about the problem got harder in any human sense. It is the same instruction, the same question. All that changed was the number of things, and the work exploded so violently that the fastest hardware we will ever build cannot be pointed at it. Mathematicians call problems like this intractable, solvable in principle, unavailable in practice. A slightly bigger question, and the answer retreats past the end of the universe. Now, nobody actually brute forces this. Real route planners use shortcuts. Start somewhere sensible, improve it, stop when it stops getting better. Those methods are fast, and they are good, and delivery companies run on them every day. But look at what you agreed to when you took the shortcut. You gave up on being certain you have the best route. You now have a route that is probably close, and nothing tells you how close, because checking that would mean finding the best one, which is the thing you could not do, which is exactly the deal you make at the microwave. 30 seconds, check, 30 more. Fast, good enough, and never exact. And there is the second reason your progress bar cannot be trusted. Even where a prediction is theoretically possible, working it out can cost more than the installation itself. So the installer does what you do at the microwave. It guesses, checks, and revises. It is not computing an answer. It is feeling its way forward. Put the 3 walls next to each other, and something underneath them comes into view. Some questions have no general method at all. That is Turing. Almost every interesting question about behavior is in that group. That is Rice. And plenty of the questions that do have a method have one that would outlive the sun. That is intractability. What they share is this. Every one of them gets worse as the question gets broader. Ask a narrow question and you are usually fine. Will this specific loop, counting to 10, stop? Yes. What is the shortest route between these 4 towns? Here it is. Narrow questions have edges, and things with edges can be checked. Ask the same question in general, for every program, for every route, for every case, and you fall off one of the 3 cliffs. That is the trade-off, and it is not a temporary state of engineering. It is a fact about what computation is. The more general a question becomes, the harder it gets to answer, until at some point it stops being answerable at all. You can feel the same trade-off in yourself. Reheating this particular bowl of pasta in this particular microwave that you have used 400 times, you are good at that. You know it takes 2 minutes and 10 seconds. Reheating any dish, in any microwave, correctly, first time, every time. Nobody is good at that, and nobody ever will be. And it is not because we lack the recipe. The general problem is not a bigger version of the specific one. It is a different kind of thing. Which brings us finally to the machines everyone is arguing about. Whatever else an artificial intelligence is, it is a program. Very large, very clever, trained rather than written, but a program, and everything above applies to programs, not to slow programs or badly designed programs, to all of them. So no system, however powerful, gets a general method for deciding what an arbitrary piece of code will do. No system gets to always determine whether another system will behave. And no amount of hardware makes a problem with 30 items collapse into one with 10. That is not pessimism about any particular technology, and it is not a prediction about what gets built next year. It is older than the field. It was true in 1936, when the machine Turing was reasoning about was an imaginary tape with a head that could read and write, and it will be true for whatever is running a century from now. None of which means we are stuck. We answer questions of exactly this kind all day long, in specific cases, by narrowing them until they have edges. That is what good engineering actually is. Not defeating the limit, but arranging the work so you never have to stand in front of it. So the next time a progress bar tells you 2 minutes, and then 17, and then sits at 99% saying unknown, it is not broken. It is standing at the edge of something a 24-year-old found in 1936, and it is doing the only sensible thing left, guessing. If seeing why something is true means more to you than being told that it is, subscribe. I'll see you in the next dimension.